Welcome back, everybody. We're going to start talking about exponential and log functions this chapter, starting off with inverse functions, what inverse functions are, how we find them, because that's the basis for how we're solving. We first got to talk about one-to-one functions, where we have one y value to each x value. So an actual function, if we were to do a graph like this, we would check if this is a function, just a regular old function, by doing the horizontal line test to make sure that no x values are repeated. For a one-to-one function, we have to do a horizontal line test, and that's going this way. The premise is still the same. We still want to only touch the graphed line one time. In this case, this parabola is not a one-to-one function because my horizontal line test touches that graph twice. How do we know if something is one-to-one? Well, we can do the horizontal line test, but there are a few different ways that we can do this. Basically, we're checking to make sure that x's and y's do not repeat. So the values of the domain have different values of the range. Besides the horizontal line test, we can start with plugging in a value. Pick any value you want. Let's say I want to say x is 4. If we pick x is 4, we're also going to pick x is negative 4. And our goal is to find out what y is and see if those y values are the same or different. If I look at function a, starting with positive 4, negative 4 times 4 is negative 16, plus 12 is negative 4. For positive 4, we would have negative 4 times negative 4 plus 12. Negative 4 times negative 4 is positive 16. 16 plus 12 is 28. These y values are different, so yes, this is a one-to-one function. The second example, we can still use 4 and negative 4. If we did that, we'd have the square root of 25 minus positive 4 squared. That's 25 minus 16, which is the square root of 9, and that answer is 3. If I plug in negative 4, we have the square root of 25 minus negative 4 squared. Now remember, we're following order of operations, so we have to do the square before we can do the subtracting. So I can't do add the opposite here. Negative 4 squared is positive 16. 25 minus 16 is still the square root of 9, and the square root of 9 is still 3. So we have different x values. One's positive 4, one's negative 4, but we have the same y value answer. And so because of that, the second one is not a one-to-one function. This is the horizontal line test that we just talked about. So any horizontal line that we draw anywhere on the graph can only touch the graph one time. We see in example A, this horizontal line they've drawn right here actually touches this graph 3 times. Now, if we would have drawn it right here towards the top, it would have passed. But remember, you have to check several different areas. And so because in this area right here, it touches that graph 3 times, even if it was only 2 times, that would mean it does not pass and is not one-to-one. For letter B, We've drawn several horizontal lines just to double check everywhere we go that it's only touching that graphed line one time. And that is the case. See, it only touches it one time. And so, yes, this is 1-to-1. In general, if the function is increasing or decreasing on its entire domain, that means it's going up, no matter if there's maybe a little bit of wiggles. Sorry, that was a bad example. As long as it's going up the entire time or down the entire time, and there's no little wiggle like this, that's a decrease. So increase, decrease, increase. If that doesn't happen, then it's 1-to-1. And so these are some examples of some functions that are 1-to-1. We can ignore this section right here. All right, so we're sitting here looking at 1-to-1 functions. We've decided, yes, this function is 1-to-1. How do we know if they are inverse functions? So let's talk about inverse for a second. Inverses are opposites. And so x plus 7 equals 4. The opposite of adding 7 is subtracting 7. And that's how we solve for x. It's an opposite operation or an inverse operation from what we had. And so it's asking us to say, how do I know if what I'm looking at is a set of inverse or opposite functions where we've done opposite operations to get to each one? We looked at this before as composition. So we're doing a composition of functions. This f circle g we rewrote as f of g of x, and g circle f is g of f of x. We want this composition to reduce to x. We're not solving. We're not trying to get x equals 9 or x equals 27. We're just trying to simplify to see if I simplify, do I get x? Just x. And if I do, then it is an inverse function. But you can only find inverse functions if you have a 1-to-1 function to start with. So let's practice. Is G an inverse of F? Are they inverses? I'm going to start with f of g of x. What is the g of x function? Well, the g of x function is the third root of x plus 1. And so this says, hey, look at the f function, and in x, put this third root of x plus 1. All right. We have x to the third minus 1. And in place of x, we have the third root of x plus 1. Sweet. So looking at resimplifying this, the third root and the third power are inverses or opposites. They simplify each other, undo each other, cross each other out, however you want to say that. That leaves us with x plus 1 and then this minus 1 on the outside. Continue combining like terms. I have plus 1 minus 1, which is 0, and that leaves us with just x. That's perfect. That's exactly what we want. That means that f and g are inverses of each other. We should also check going the opposite direction of g of f of x. And so in this composition, we're starting with, what is the f function? Well, the f function is x cubed minus 1. Take that, plug this f function into the g function right there for x. So we have the third root of x cubed minus 1 plus 1. Well, these parentheses we don't need right here because there's nothing on the outside of the parentheses to distribute. Combine like terms, we have negative 1 plus 1 is 0. That leaves us just x cubed underneath there. And like we just said, the third root of a third power, those are exact opposites and undo each other and simplifies to just x. This is how we say that yes, these two are inverses of each other. That's proving it. On these blanks here, the domain of the regular function is the range of the inverse, and the range of the original function is the domain of the inverse, because again, they're opposites of each other. We've talked about what inverses are. We've talked about how to prove two things are inverses, but what if they give us something and say, hey, now I want you to find the inverse because we don't know what it is yet. The first thing you have to do is check that whatever they give us is 1-to-1. That means no repeating x or y values. It's got to pass the vertical and horizontal line test. All right, so looking at the f function, starting with my x's, I have -2, -1, 0, 1, 2. That's great. Nothing there repeats. We're good for that. Y's, I have 1, 0, 1. Uh-oh. I've got 1s that are repeating up and 2s that are repeating. So because of repeating y values, this is not 1-to-1 and has no inverse. Let's take a look at the second one, the g function. All right, I have x3, 0, 2, 4. All right, 1, 2, 3, 0. None of that's repeating. So this is 1-to-1. Now that we know that it's 1-to-1, we can find the inverse function. So we start with the notation that negative first power says, hi, I'm an inverse. And then when we're given a list of values, we're swapping x and y. So 3, 1 becomes 1, 3. 0, 2 becomes 2, 0. 2, 3 becomes 3, 2. And 4, 0 becomes 0, 4. And that's the inverse function. Take a look at our hurricanes here. Our years, we have 2009, 10, 11, 12, 13. Nothing repeats there. Number of hurricanes, 3, 12, 7, 10, and 2. Nothing repeats there. This is 1-to-1. And so to make our new table for our inverses, we're going to have hurricanes on the left side, and then year on the right side. 3, 2009. 12, 2010. 7, 2011. 10, 2012. And 2, 2013. Taking the X and the Y column and making them trade spots. So if we're not given a table and we're not given a set of ordered pairs, now what do I do? Well, if we verified that we have a 1-to-1 function, Okay, we've graphed it in our graphing calculator and had it pass the horizontal line test. We've picked an x value, positive and negative, and made sure the y's don't repeat. Once we verified that, then we swap the x and the y itself. Solve for y again using backwards order of operation, PEMDAS backwards, or SADMET, and then replace y with f of -1 to show this is an inverse, or g of -1, h of -1, whatever the original function notation was. All right, I'm going to start with example A, and if I put that in my graphing calculator, the graph, excuse me, looks like this. And so doing my horizontal line test, it passes and is 1-to-1. Remember, f of x is the same as y. So start with swapping the x and the y. It's literally putting x in the spot where y was and y in the spot where x was. And then backward order of operations to get y alone. Our first step would be to subtract 5. And then divide by 2 on both sides to finish getting y alone. And so x minus 5 over 2 is our inverse function. And we note that with that f to the negative first. Letter B. If I graph that x squared plus 2, I get this. It's a parabola, and it does not pass the horizontal line test. That means this is not a 1-to-1 function, and there is no inverse. So I can't go any further. Letter C, if I plug that into my graphing calculator, I get this. And that does pass our horizontal line test. Remember, f of x is y, so this is what we have sitting there right now. Y equals x minus 2 to the third power. Swap x and y. Get y alone. Well, our first step is to get rid of that third power. The opposite of a third power is a third root. So we have the third root of x is equal to y plus 2. Subtract 2. Be very careful when you do the subtract 2. You want to make sure that minus 2 does not look anything like it's going to be underneath that radical. So I try to separate that out really far. Or remember, we can rewrite a third root as the 1/3 power, power over root, to make it look like that. And then there's absolutely no question. We write f to the negative first power there, and that gives us our inverse function. We are going to skip example 6 here, head over to example 7. So we've talked about finding inverse functions from a table, from a list of ordered pairs, and from an equation. So what happens if they give us a graph? Well, a graph isn't so much different than a table. The two ordered pairs we have in this graph on the left are 3, 1 and -4, 0. So the inverse, remember, we take the ordered pairs, swap x and y. 1, 3 and 0, -4. So if I plot 1, 3 and 0, -4, draw that line, now we have a graph of the inverse function. In the second graph, the ordered pairs they give us Looks like down here we have 0, 0. So we have 0, 0, 1, 1, and 2, 4. 0, 0 flipped around is still 0, 0. 1, 1 flipped around is still 1, 1. But 2, 4 is now 4, 2. So I'll put that here. And there's our new inverse function graph. Example 8, we really don't solve this any differently. The only part that we would have to worry about in this graph is that the domain restriction will change our domain of our inverse function as well. But if all we're trying to do right now is find the inverse function, we're not going to worry about the domain, we're just going to find the inverse function. Then if I graph this, it's going to look like that. And even though it kind of looks maybe on our graph like it flattens out, that's just because the decimal is so super small when it's changing. But it does pass that horizontal line test. So this is a one-to-one function. Remember, f of x is the same as y. And so x and y are trading places. Get rid of the square root. The opposite of a square root is a square or a second power. We have x squared is y plus 5. And then we're going to subtract 5 from both sides. And we have x squared minus 5 is our inverse function. Our last part is just a summary of everything that we've talked about. So if we find out that a function f is 1 to 1, then we know that an inverse exists. We can find it. The domain of the original function is the range of the inverse, and the range of the original function is the domain of the inverse. That's taking the x and y columns or coordinates in our ordered pairs and flipping them the opposite way. If we have an ordered pair on a graph of AB, then the inverse would be BA. And they are reflections over y equals x. To find the equation for an inverse, replace f of x with y and change around x and y to solve for y again. That gives us the inverse. This is the end of our notes. Thank you so much for joining me. Have a great rest of your day.